Today's lesson, well, I settled for the title Circular Functions, but I guess it could have been called a lot of different things. It could have been called Trigonometry Without Triangles. It could have been called Trigonometry Revisited. And the whole point is that much of what today's lecture hinges on is a hang-up that bothered me and which I think may bother you and is worthwhile discussing. I remember when I was in high school, I asked my trigonometry teacher, why would I have to know trigonometry? And his answer was, surveyors use it. And at that particular time, I didn't know what I was going to be, but I knew what I wasn't going to be. I wasn't going to be a surveyor, and I kind of took the course kind of lightly and really got clobbered a year or two later when I got into calculus and physics courses. So what I would like to do today is to introduce the notion of what we call circular functions and point out what the connection is between these and the trigonometric functions that we learned when we studied the subject that we call trigonometry and which might better have been called numerical geometry. Let me get to the point right away. Let's imagine that I say circular functions to you. I think it's rather natural that as soon as I say that, you think of a circle. And because you think of a circle, let me draw a circle here, and let me assume that the radius of this circle is 1. In other words, I have the circle here, x squared plus y squared equals 1. Now, the thing is this. When I talk about, and I'm assuming now that you are familiar with the trigonometric functions in the traditional sense. And in fact, the first section of our supplementary notes in the reading material that goes with the present lecture takes care of the fact that if you don't recall some of these things too well, there's ample opportunity for refreshing your minds and getting some review in here. But the idea is something like this. When we're talking about calculus, we talk about functions of a real variable. We are assuming that our functions have the property that the domain is a set of suitably chosen real numbers, and the image is a suitably chosen set of real numbers. We do not think of inputs as being angles and things of this type. And so the question is, how can we define, for example, let's call it the sine machine. Let me come down here. I'll call it the sine machine. If the input is the number t, I want the output, say, to be sine t. But you see, now I'm talking about a number, not an angle. Well, one way of doing this thing visually is the old idea of the number line. Let us think of a number as being a length, the same as we do in coordinate geometry. Okay, we mark off lengths along the x-axis and the y-axis. Let me think of t as being a length. As such, I can take t and lay it off along my circle in such a way that the length originates at S and terminates, shall we say, at some point P whose coordinates are x and y. Now notice what I'm saying here. I lay the length off along the circumference. I'll talk more about that a little bit later. Now, so far so good. No mention of the word angle here or anything like this. Now, wherever t terminates, and again, conventions here, if t is positive, I lay it off along the circle in the so-called positive direction, namely, what, counterclockwise. If t is negative, I'll lay it off in the clockwise direction, etc. The usual trigonometric conventions. Now what I do is at the point P, I drop a perpendicular. Okay? And I define the sine of t to be the length PR and the cosine of P to be the length OR. In other words, I could write that like this. I could write down that I'm defining sine t to be the length of RP in that direction. Meaning, of course, that this is just a fancy way of saying that the sine of t will just be the y-coordinate of the point at which the length t terminates on the circle. And in a similar way, cosine t will be the directed length from O to R, or more conventionally, the x-coordinate. Now notice I can do this with any length. Whatever length I'm given, I just mark this length off. It's a finite length. Eventually it has to terminate someplace on the circle. Wherever it terminates, the x-coordinate of the point of termination is called the cosine of t, and the y-coordinate is called the sine of t. And notice that in this way, both the sine and the cosine, are functions which map real numbers into real numbers.